Okay, so I guess I probably want to switch to the presentation on this. Okay, so I think that's better. So we have everyone on this screen, basically on the PowerPoint slides. So, okay, so I would assume that everyone has the course syllabus. And also, like I said before, usually I post course material on Blackboard. I would assume that you have access to the Blackboard, to the course material, to view the course documents, and also the homework assignment, including computer assignment, which I probably will put that on Blackboard. And also, you will find some useful information under external links, where I post some advanced material related to optimization theory and also some electronic version of the textbook that for those of you who are keen to the mathematical details of the optimization technique, you may want to read. And also, I have maybe 8 to 10 books on reserve at library, which usually I feel are useful supplementary readings for those of you who want to, especially for those of you who are doing research related to finding appropriate optimization technique that you want to use. Please, also you can check your library website and find out the books on reserve. You can read, you can borrow it for as long as 3 days, but you have to return it so that other students can usually check that as a reference, okay? And also for the course syllabus, I think the textbook, which is this adventurous third edition, I think some of you may use the second edition because it's less expensive, and that's fine, but usually I would want to make sure that you understand about the assigned course problem. That's according to the third edition. Usually I put the page and the problem number on Blackboard, so please check with your classmates on this. For the readings, I would say most of the required knowledge for taking this course is usually advanced calculus, which I will briefly review from the beginning of the lecture. And in addition, I would say that we can basically interact during this, I would say, less than 3-hour lecture. And also, we may have some interim break for about 5 to 10 minutes, just not to get bored. Okay, so any questions up to this point?
Is the book available in the bookstore?
Yes, I think so. Okay, and any other questions? Okay, so I guess let's get started. And for this course, of course, it's about engineering optimization techniques. And I would like maybe to ask each of you, just give me some brief description what you have in mind about engineering optimization. You think it's applied math? It's basically what do you expect from this course? And let's be a little bit brief. So I will start from the other end. Let's start from Reston, please.
It's a lot of geometry.
A lot of
That's geometry.
geometry. Okay.
Yeah.
About what?
Like you have these odd-looking functions and you have to
Okay.
minimize it or something.
Okay, find the maximal, minimal of some bizarre objective function. Okay, good. And Mr. Liu?
Hold your button down. I forgot.
Okay. If you want, you can press the touch button so that the other end will hear you. Oh, thanks.
I think it's mainly revolves some questions, and because it's called engineering applied engineering optimization techniques, it probably involves some practical problems for the people to understand how to use the techniques here.
Okay, and very good. So, Mr. Gang Liu.
Yeah, I'm thinking maybe just one example, like the Formula 1 racing car. There are a lot of parameters balancing. You need to balance each other to get the fastest speed.
Okay.
That is the example of optimization.
Okay, so
I think.
yeah, of course, there are many engineering problems require you to find the best solution when you have flexibility in changing design parameters somehow. Okay, and Mr. Xu.
I think this course related to the use some minimal cost to get the best some like I don't know how to say. I mean, solve as the optimization problem like that.
Okay.
The minimal cost, but get the best like benefit on it.
Okay, and Mr. Wu.
I think the optimization is to find some maximum and or maximum value and some conditions restrict.
Okay, and there's some constraints.
Yes.
Okay, so yeah, of course, usually later we are going to say what are those constraints, how to put that into mathematical form so that we can define the problem better. Very good. Okay, so we will switch to the right-hand side. Yeah.
I think that what I want to get out of the course is pretty much to learn how to pretty much how to set up problems to, I guess you can say, quote unquote, find the best product at the minimum cost.
Okay, find the best product of the minimum cost. Well, for some engineering problem, if you have the concrete problem, we are going to try to talk about that, but this course usually is not really just about formulating the optimization problem. It's mainly about how to solve some well-formulated optimization problem. Okay?
Okay, I'm Nick Musmisi. I work for Entity Corporation. One of my primary job functions is a control engineer. So I've had some optimal control in the past.
Okay.
And what I want to do is, my objective here would be to get back on track and review some of the mathematical expressions and whatnot. Also updating the skills as far as MATLAB, using some of those simulation techniques and maybe applying them in my job as far as maybe simulating some control actions. Or there's very many applications when it comes to optimal boiler control, particularly now that we're doing like NOx reduction and we're looking at different processes, and then you might want to judge whether those processes are really going to give you the biggest bang for the buck.
I see. Very good. And also,
and by the way, I've had some artificial intelligence background too, so I'd like to delve more into it instead of letting the other guys do all the.
Okay, that's good. And also, by the way, I think this course is not really about optimal control, but we will touch a little bit about some formulation if you have some optimal control problem, how to solve certain type of optimal control by some efficient computing technique, which, for example, includes dynamic programming and some other techniques. I'm going to mention about that.
To me, optimization means finding the maximum or minimum of some real valued function, like maybe defined in terms of a generalized norm, where the function may be a vector valued function, but it maps to real value to the real space, and under various constraints, depending on whether the maxima or minima exist in that space.
Yeah, I can see that's very formal mathematical description of the optimization.
And to me, and I want to learn optimization, especially because there is actually because of a very, very good theoretical mathematical base it has. Means a lot of real analysis involved in this. So
okay, good.
So.
For me, this is a quite a new area. I know a little bit, not too much about this, but basically I think this is find a best way to find the solutions. Some problem maybe need to find the minimum values, and maybe find the maximum. Basically, is a best solution for a problem.
Try to at least define some problem first, and then also define what do we mean by best.
Yeah.
And then also, I think most of you mentioned that we have some real value function and we want to find the peak, that's the maximum. That's easy. And sometimes, for instance, if you want to find the best plan in order for you to get an A out of this course, then that optimal strategy for you will be quite challenging because it's not really clearly formulated mathematical problem. But we will have to find some middle ground as an engineer how to formulate your problem in a mathematical way that we can use efficient computing algorithm to solve. Okay, so get to last student.
I hope to gain from this course how to find local optimum, what conditions this local optimum will be a
Global one,
solution.
okay.
And also, given how difficult it would be to obtain a global solution.
Okay, very good. I think that's very keen question. We hope after taking this course, all of you can at least get a piece of the answer to the big picture, how to really find the global optimal solution for some very challenging engineering problem that you have to optimize in real world. Okay, so maybe let's try the other end, see if we can get some input from Stanley Space Center. Hello?
Yeah, for me, I want to know the right optimization technique, because there seem to be a lot of different techniques to use for a given problem. Another thing for me is how to best formulate the minimization function that I'm using in the optimization, and then also how to fine-tune the parameters. I've used MATLAB and I've used some of the functions in there already, but I want a better understanding of what I'm doing with it.
Okay, great. Okay, so I guess that's a good opportunity at least for students to get to know each other a little bit, and then during the whole semester I hope that we can have some more interactions through after-class discussions, or maybe even use course Blackboard. I would assume that you are aware there's a so-called discussion forum where you can post your questions, comments, so that maybe I can respond, and also other students can make some input to it. And I just realized that there's a problem of the course Blackboard after upgrade. Whenever I try to open up a blog or maybe write a journal so that everyone can see some of my personalized account about optimization, the computer speed is extremely slow. I'm not sure it's just me or because of the upgrade of the Blackboard. So we will have to explore further about that, but just let me know if you do experience difficulty using course Blackboard. So we will figure out some best thing about this. Okay, so now let's get into the real contents of the optimization. I guess before we really talk about optimization problem, today we are going to review some basic calculus just so that later you won't feel overwhelmed by some bizarre terms that when we say objective function, feasible solution, constraints, convex, concave, property of a function, you won't feel that's too much. And also I hope that after this class, please try to find the textbook, and no matter which edition you have, try to buy either from the bookstore or maybe you can buy online for used textbook with less money that you need to invest on this. But this is a very good textbook that you can read. It's not very mathematical. It has good engineering motivation on different type of problems. So I want you to read like the first part with mathematical background, which I cannot cover everything, but I want to cover just the basic elements so that we can move on to just the formulation of optimization problem, give you some examples on how basically we try to convey the real problem into some mathematical optimization problem. And next time we are going to talk about specific mathematical tools or algorithms to compute the maximum or minimum solution to some optimization problem. So let me try to switch to desktop. And I think some of you already print out the lecture notes, which you will feel less fun when it comes to do some exercise on the problem. But of course, it's easier to see that in order to really find the optimal solution, we need to rely on the property of the function in itself. Okay, so here we say there's some kind of continuous function f of variable x, and remember this x usually it's a scalar variable, but sometimes it can be a vector, and still we can say, of course, the whole function has to be it has to give you some real number that you can compare. It is larger when x equals to 5, it's smaller when x equals to 4, so on and so forth. And one important concept is about the limit. When x approach to a, and let's say this f of x will be equal to c, and what does that mean? Well, the limit is something like, of course, the easiest way to say the limit is something like, okay, so let me just say x equals to a and plug that in. But usually that's not really the mathematical concept of the limit. Okay, so what I'm trying to say is that, hello? And what I'm trying to say is that in order to really understand about the limit, you have to think about, you have a sequence of numbers approaching to that value. For instance, I can say if I want a equals to 1, and then maybe I say 0.9, 0.99, 0.999. I have some sequence eventually approaching to that value, and then what's the limit? And that's the basic concept about this. And think about this limit, you can also let this value approach to positive infinity or negative infinity. Okay? So that's the concept. You want it to be closer and closer to a, but not really equal to a. And then you want to know what happens in the limit. And it is also possible that sometimes the limit doesn't exist. Okay? For instance, you may say, well, if x approach to 0, what's the limit 1 over x? Doesn't exist. Why? It blows up in what sense?
Obviously, as the number in the denominator gets smaller, you know, it's going to approach 0, right?
Okay.
So the value is going to get larger.
Larger, do you mean positive or negative? Well, depending on which direction it approaches. Yeah, yes.
For 1 over x, from the left side you approach negative infinity, from the right side you approach positive.
Okay.
They don't agree, so the two-sided limit does not exist.
Okay, very good. And what about this case? If x approach to infinity, what's the value of sine of x? Yes. It will, okay, it will oscillate around within -1 to +1, but what? Well, doesn't get to a fixed value. So we say the limit doesn't exist. Okay? And well, limit doesn't exist. We also can realize that in some cases, the right or left limit may exist. Still from this example, like what Sarah just mentioned, that if you take a positive sequence approaching to 0, then this will be positive infinity. If you take a negative sequence approaching to 0, then it will be minus infinity. So basically, the limit concept is about just a sequence of, you have to construct a sequence that approach to something, okay? And of course, there's another aspect that I may want to mention to you, which I'm not sure if I can. Basically, I will try to see if I can connect to document and local. Okay, so let me try this. I think, how many of you heard about, for instance, let me see if I have something that I can write it down. Okay, so for instance, we have like the maximum of some sequence, right? I can say if this sequence is xi, I from 1 to n, that means I want to find what? The maximum value of this sequence. What if this sequence is infinitely many? If this sequence, I will say supreme for this sequence, xn, and in this case, n can go from 1, 2, 3, 4 until infinity. Then, of course, I can talk about the limit, right? And sometimes I want to know in the limit what's the maximum, what will be the maximum of that, okay? And sometimes this is not really very clear what it means, right? For instance, if you have a sequence, you could end up with somehow certain part will approach. For instance, you may say a sequence is like the odd number of n, let's say, is, for instance, 1 plus this, when n is odd. Okay, and then you may say when n is even, is, let's say, 2 minus, this is n is even. Okay, so that's also a sequence, right? Okay, and can I find the limit of this sequence? No. Okay, because for instance, for the sequence where the number of n is odd, I know the limit will be 1. For the sequence, when n takes even number, the limit is 2. They are different. Can I find the maximum value, which is 2? Okay, but that's also in the limit, it's 2, right? Do you agree? It will never be 2 until n approach to infinity and take even number. Do you agree? And in that case, how do we say that? For instance, we say the limit for the supreme of this sequence n is 2, right? This equals to 2. Make sense? So for instance, if you see the limit that has this supremum on top of that is about this. Okay, and similarly, if I want to find the minimum, I should write limit of this, right? And in this case, which is what? In this case, it is 1. Okay? Any questions? I think these are just some mathematical language to talk about maximum or minimum. Sometimes it's not so obvious when we say, okay, that's the maximum. Well, it because of the concept of limit. Okay, so I hope we can now switch back to the computer. Okay, and let's see. Of course, another important property about finding the maximum and minimum is about the property of the objective function, this f of x. And a function is a continuous function. That means what? For any point. Okay. Okay, for any point, you can basically find a sequence that approach to that, right? Okay, so that's like the basically you can say intuitively a continuous function means that you can draw it without breaking, without moving your pen. Okay, very good. But that's just intuition, because sometimes you may have some situations you have to pay a lot of attention. And also sometimes we have to talk about whether it's continuous, whether it's differentiable or not about a function. And here we say if a function is not continuous at a particular point x equals to a, if what? Well, if you can, for instance, you can find 2 different sequences approach to A where the limits are different, right? Like what we just mentioned in some examples before. Okay, so here's one example. That's the real function defined this way. When x is from 0 to 100, f of x equals to 25 multiply x. And when x is from 100 to 200, it equals to 20 multiply x, and when x is greater than 200, f of x equals to 15 multiply that. Yes?
Dr. Chen, concerning your definition of discontinuity.
Okay.
What if you had it just a hole in the function? Wouldn't the limit still exist?
Can you give an example about that?
Example, you have f of x
Okay.
equals x times x minus 1.
Let me see if I can write it down and show to everyone on this example. Okay, so you want f of x equals to
X times
x,
parentheses x minus 1
x multiply x minus 1, okay,
over x minus 1.
over x minus 1.
Wouldn't the limit exist, still exist? You'll have a discontinuity at 1, but the limit still exists.
Okay. But in this case, I would say, how do you define that? The value for f of x when x equals to 1.
Wouldn't the limit be 1? I mean,
it's x.
If f of x is x, here the
Yeah, it's kind of x.
because x minus 1 is x minus 1 cancel.
if you plug that into a graphing calculator, it'll have a removable discontinuity at x equals 1.
Well, I would say you need to define what the value f of x should take when x equals to 1, because otherwise you can easily say x minus 1 cancels from the numerator and denominator, right? But on the other hand, if you write this way, it means that it's undefined on the denominator. You cannot say infinity over infinity cancel with each other. So depending on the context. And this course is not really pursuing for mathematical rigors, but try to at least use mathematical language to describe about optimization problem. I hope that will make some of you feel comfortable, but of course, due to limited time and effort, I will have to encourage those of you who are mathematically keen to the rigorous description, look into some supplementary reading that I post on Blackboard under external links. Okay, so, but thanks for the question, and that's a very good one. And in this example, is this function a continuous function? No. Where are the discontinuity points? At where? At 100? At, well, 0, we don't know what happens when x is less than 0, so we cannot say too much about that one, because it's just a starting point. Okay, and 100 and 200. Okay, very good. So obviously, you check the limit on one hand and the other hand, and the limit on these 2 points doesn't exist. So in that case, we see 2 discontinuity point locations over there. Okay? And derivative, that's also an important mathematical property we are going to use in order to design optimization algorithm. Of course, if a function is not a continuous function, we cannot talk about the derivative. But of course, in the abstract sense, later we're going to talk about even if you have discontinuity, you can still have some kind of, maybe not derivative, but at least some direction you can define some kind of gradient projection. But let's not get into that. First, let's talk about the derivative. What's the meaning of that? Intuitively, you can think about just at value f of x equals to a, at this particular value, if you want to know the derivative of that, which is defined by this, the limit of this increment, delta x approach to 0, what's the difference of the function value when you have small increment? Okay? So by doing that, if you know how to use the concept of limit, you can really do derivative. And most of the time, you don't have to derive from the beginning. You just what? Know the answer. But sometimes, because the function is too complicated, you don't really have the analytical form for the derivative. What do?
You do it numerically?
You do it numerically, like what?
Make your delta of x increasingly smaller.
Okay, and then
See if it converges.
see if using a computer the change of this increment is small, then you'll say numerically I get the derivative, right? For instance, you'll say if I change this from 0.0001 to 0.00001, this increment doesn't change too much. I say, well, maybe that's what I get, with some error, numerical error, of course. But most of the time, you really need to know some important function how to really find the derivative. Like in advanced calculus, basically you have some table on the differentiation and integration of some important mathematical functions. So let's do this. Find derivative with respect to this variable p. What do you do?
Using the power rule there, so as far as that goes.
Okay, so in this case, how do you take derivative? Because it's p multiply e to minus p, so you do what? First derivative with respect to p, then it's just e to minus p, right? And then the other one is p multiply, and derivative of e to minus p is what? Minus of e to minus p. So because of this, we have two terms with respect to first term like this and the other term like this. Any questions? Okay, so I think that's easy. And another important question is, for instance, is this function like monotonously increasing or decreasing? Does it have any maximum and minimum? That's something we want to talk about in optimization. Okay? So for instance, if you know the derivative is positive, what does that mean? You have a slope that goes like this. You know the function looks like what? Non-decreasing, right? If you have the derivative that's negative, then what? You know, somehow the function will look non-increasing. I'm sorry? Well, later we're going to talk about that. For instance, sometimes we cannot say for sure by just looking at the derivative. We have to first think about, we have to think about some other properties. Maybe like what you suggested, look at second order derivative. Okay, so for what value of p is this function f increasing? And how do you know?
Well, you'd have to set it to, you mean as far as increasing?
Yeah.
I was thinking like if you got to a point where you put a 0 to it.
Okay, so of course you can check first, just starting from p equals to 0, this whole thing is what? 0. And then you know that when p is positive, this function is positive, right? And then when p approach to infinity, because of this exponential function, it will approach to 0, right? So it will somehow goes up and then down, and then you will know that somehow this thing, what? You set the derivative equals to 0, and then you get the range where it's positive, where it's negative, right? And then basically that's the idea. And later we're going to say, well, that's important property. You try to find the maximum and minimum. Okay, very good. So how do we find higher order derivatives? Well, if you take first order derivative, if the function happens to be differentiable, you can keep doing, right? Just go as what you want. And of course, you can take second order derivative, which sometimes we use double prime. Sometimes we just put a parenthesis where we indicate that's the order of the derivative. And usually it's evaluated at different values in order to see that particular point is maximum or minimum. Okay, And we can define nth order derivative if it exists. We just try to compute that. Okay, and for the previous example, we already did the first order derivative. I think if you recall, it's in the previous slide, we have this, right? And then we take another derivative, then this will become what? This will become minus 3000 e to minus p. And what about this one? This one is actually minus of this, right? So you can just change the sign, right? So that's very convenient. By doing that, we end up with somehow something like this. This is minus 3000 e to minus p, and then you have this. And of course, you can simplify the expression a little bit by just collecting some common terms and get to this. Okay, so another example that sometimes we try to approximate a continuous function by so-called Taylor series expansion. Okay, and what does that mean? That means basically we can expand a function based on what? Based on its different orders of derivatives evaluated at a particular point. And then we can basically expand the function, maybe, for instance, in some way like a polynomial. For instance, if I have a sine of x, for instance, if, let's say, if I have sine of x, let's say if I want to expand this for x is small, let's say close to 0, what should I do? I think some of you may know that it's approximately equal to what? Maybe x, right? And how do I get that? Well, in fact, it's like you evaluate at sine of 0, which is 0, and then you have what? Derivative of sine of x, which is cosine, evaluate at 0, which is what? 1. So, and then x, and then what about second order derivative? Cosine, and then you do another. It's well, minus sine, but still when you evaluate at x equals to 0, it's 0 anyway, so we don't need to worry about that, but we need to worry about what? And the next term will be what? Another derivative, which will give you what? Because it's minus sine and then minus cosine. So minus cosine is minus 1, and then but you still have what? One over. You think it's what? You need to have, because this is x to the power of 3, right? And then it's 1 over 3 or 3 factorial? I think it's 3 factorial. Okay. So which is what? And then plus, you can keep doing that, right? Is this 3 factorial? Okay, so let's go back to expand e to minus x at x equals to 0. Okay, so in this case, you can see that first order derivative is just minus e to minus x, and then take another derivative, you'll get to itself. Okay. So this holds for any small interval from 0 to some value b. And also you can see that when x equals to 0, this e to 0 is 1, and derivative of the first order derivative evaluated at 0 is minus 1, and second order derivative evaluated at 0 is 1, and the 1 minus 1 alternates, right? So you can see that this if you expand around some neighborhood close to 0, it's what? 1 minus h, and then this is h squared e2 minus p over 2, right? And then what? Minus, yeah, of course, this is approximation. This should be approximately equal to that. And then plus, if you want, the third term should be what? Minus what? H to the power of 3 divided by 3 factorial. Okay, so basically I don't expect you to memorize all the mathematical formula, but when it comes to calculating the optimization problem, definitely you need to have a reference at hand so that you can figure this thing out. Okay, and this is about just scalar case. Can we expand this to vector case where it's not f is not a function of single variable but multiple variable, a vector x? In that case, what will happen? Well, if we have a function that involves multiple variables, can we talk about, for instance, derivative, continuity? Yes. And basically, we just extend the concept to what?
To a surface.
To some kind of surface, curved surface, and things like that. But the key ingredient in that is you take derivative with respect to each variable, which is considered something like partial derivative, right? And if you consider a collection of these partial derivative, we call that what? The gradient with respect to a vector of the variable. And of course, second order derivative will be what? Because you can have all parents, it will not be like a vector, it will be what? It will be a matrix. Like for instance, if you have two variables, then you can do partial for 1 and then 1, so you have like derivative 1, 1, 1, 2, 2, 1, 2, 2. So it looks like what? Matrix. Yeah, and we call that a Hessian matrix. Yeah, so, I'm sorry? Jacobian usually is a name for, later we're going to talk about that. I think that's also an important mathematical concept. A Jacobian matrix is about if you have, let's say, two functions of x1 and x2, then of course you can basically talk about the gradient with respect to the first one and the second one. And then you can have so-called Jacobian. And usually it's about something like you have function of vectors, vector variables. Okay, so I think we should start from something relatively easy to understand. We first talk about the partial derivative. Okay, so if you have a function that involves n variables, x1 through xn, and then we want to talk about derivative with respect to a particular variable xi, in that case, what we need is what? Well, just by definition, it's just the increment with respect to this variable and keep other variable more or less fixed, and then to take the limit for that. So that's the definition of partial derivative. And most of the time, we don't really do that by hand. Either we know the function we can easily compute using mathematical property or table lookup, or we have to write a computer program to numerically compute this. So let's just do some exercise for this very quickly. So first problem, find the limit of this function k multiplied 1 minus e to minus cx as x grows to infinity for some positive value of c. What's your answer? Well, this term eventually will approach to 0, okay? And that's good. And the second problem, let's say find all first, second order partial derivative with respect to x and y. Okay, so let's do partial f, partial x. What do you get? 2x e to power of y. And partial f, partial y is the same, okay, because what? This is e to power of y. And then, of course, you can figure out partial x second order. You have what? Partial x second order derivative and partial y, and also partial x, partial y, right? Second order derivative. And last one, let's try to find the third order Taylor series expansion for the log function around 1. What do you do? Derivative of a log function is what? 1 over x. And then if you want to take another derivative, minus 1 over x squared. Okay, so just keep going. And then what? Write down the Taylor series expansion, evaluate at x equals to 1, and then you just do a polynomial function x minus 1 for this. Okay, so here's another way to write. Basically, you can say it's f of 1 plus some increment h, where you can say this is valid for some increment of h at small values. And look at here, this is basically h squared over 2h to the power of 3 over 3, and so on and so forth. Okay, so this is important concept. Can you do Taylor series expansion for like a function of vector variables? And the difference is that first order derivative will involve is what? Somehow maybe you have to expand to some matrix form where you need to use gradient. And also you need to consider about second order derivative will involve with Hessian matrix and so on and so forth. So I would like you to read the textbook and then fill in the gap that this basically can be extended to the vector case, because that's important. Another important concept is called the chain rule. For instance, if you say y is a function of x, x is a function of t, if you want to take derivative of function y, f of y with respect to t, then what do? You first take derivative with respect to x, and then x with respect to t, and then just you keep going like a chain, right? And this also is applicable when you have some complicated function, you can do that. Okay, so we are not going to, okay, so let's take 5 minutes break, and then I think that's pretty much about the basic calculus, and then we are going to talk a little bit about the real meat of optimization problem. Okay. Hi, so you're good from the other end? Hello? Any questions?
Oh, yes, sir. Yes, sir. I'm fine.
Okay, good. And feel free to ask questions if you need, or if you want to have any clarification from my end.
Yes, sir, I will.
Okay, thanks.
Thank you.
Well, I know it's not easy. Well, yeah, I also feel it makes me nervous. If it's publicly available, then cannot say something arbitrary. I mean, I don't want to look.
Yeah, exactly. Everyone can.
Well, I hope later there should be some restriction on the access to the material, and also I feel there's a pressure. For instance, you guys may not want to ask some questions. You may say, well, what if this is recorded and I didn't behave very well? I mean, I feel sleepy at that day. And there should be, well, I don't know. I feel there should be some way we can at least restrict certain part of the access, or maybe have some clipping on the interactive part.
Human resource to clip it, to add it.
Yeah. And also another, to look at the bright side, who cares about a video file? I mean, after 20 minutes, it's so boring. It's about taking limit, calculating Jacobian, and then they say, forget about that. There's no hard student sitting in the classroom. I don't care. It's not Paris Hilton or Brad Pitt. So. Okay. Yeah, that's something I may have to use the mouse, I guess. Yeah. Yeah. Yeah, I will try. Can we change the light from here? Oh, you mean the? Well, here, let me see if I can dim the light somehow. Let me try. It is a little bit better. Of course, maybe, I think. Well, I know, it makes me feel more comfortable hiding in the shadow so that the instructor will not, well.
Actually, 5 minutes, or you got a timer going on?
I'm sorry?
You got a timer for 5 minutes?
Well,
5-minute break, you said, right?
Yes.
How's your day?
I saw this morning. It's only like Facebook.
Well, then you can surprise them and tell them I'm taking the class.
Sure, I'll let it know.
I told them I would do it.
Yeah. They can take this class, but I would need it.
Well, no, I would start taking classes. So I can eventually take some courses.
Okay.
But I know he's not going to be ready for any power classes for a while. Hopefully next semester.
And this is maybe not light enough. The camera has the problem in focusing.
It's good enough though.
Oh, you mean from my end?
Yeah,
Well,
your picture is not clear.
well, that part I don't care too much because usually when you sit in the classroom, your focus it should be something else. Can I switch? Desktop. Okay. Okay, desktop.
I have a question for the students here. Y'all probably use MATLAB all the time, but to go in and order the MATLAB, how do you give them a credential to get the student version downloaded?
Oh, I'm sorry? Yes. Okay, thanks. Okay, yeah, thanks.
I just ordered it and I haven't received it yet, so.
Actually, we have a copy from, a license copy from the university.
Yeah, it was $100.
Well, in fact, I have the license copy for the whole toolbox set. But because it's limited only for research purposes, I'm not supposed to redistribute. But on the other hand, I think most of you probably have at least license copy to the university computing device. So.
Well, I just ordered mine about a week or so ago.
Okay.
It hasn't come in, but one of the things I didn't do is when I ordered it, it asked you for proof that you were a student, so you can get it for $100.
Okay.
I didn't enter that in because I didn't have the information with me at the time. But I have to go back in and make sure. I have not received it yet.
You took your money?
It took my money. I got a receipt.
Well, shall we continue? Okay, so in optimization, I think we first need to just set the tone, like what are the optimization problems? And how are we focusing on certain type of problems to solve that we are going to solve. In optimization, I think we first need to look into the problem itself and like a linear problem and non-linear problem, optimization problem. And some people say linear programming or non-linear programming, and that's just focusing on the particular optimization technique we are going to use to solve the problem. So we can say, well, in general, linear problem is relatively easy to attack, and non-linear problems are quite challenging. And optimization problems, you can say we usually look at what? The objective function and constraints. Okay, objective function, if it is a linear function of the decision variables, and decision variable is something like if you have f of x, and in this case x has to be a vector. And then this f of x is a linear function, which means what? It equals to just a linear combination of those decision variables x1 through xn. And that means the objective function is linear, and also the constraints are linear. In this case, constraint means what? Something like maybe x1 plus x2 cannot be greater than 5, and so on and so forth. And those are linear constraints. You can say, for instance, x is within 0 to 5, x1 is within 0 to 5, x2 is also within 0 to 5. That's also linear constraint. Can you see that? Yeah. Because that's inequality constraint, but you can still, by manipulating that, you can say, put that, for instance, you can say x is greater than 0, minus x is greater than 5, and so on and so forth. Basically, you can manipulate those so that the objective function is linear and the constraints are linear. Then this is called what? A linear program, a linear optimization problem. People call that linear program. And if the objective function is non-linear and the constraint is linear, is it linear program? No, it's non-linear. If the objective function is linear but the constraint is non-linear, is it linear program? If the objective function is linear but the constraints are non-linear, is it a linear program? No, it is still non-linear program. Okay, why we want to identify for linear program? What's special for linear program? They are easy to visualize. Well, what else? I'm sorry? Okay, so for linear programming, you know that there exists some kind of algorithm that can solve the problem efficiently. And why? Because first we want to make sure that there exists like a unique optimal solution to that problem, right? For instance, you have an objective function, you want to find the maximum, usually you can. If you have many constraints, sometimes you don't even have, it is possible you don't even have a feasible solution.
In other words, you may not have a minimum or a maximum.
And sometimes you don't have a minimum or maximum. You first got to make sure you have a solution.
Constraints are like this, and you want a slope or a curve, like you'll never find
a
minimum point.
Very good. Well, that's a very good comment. And first thing we want to make sure there exists. And then we can say, how can we find the minimum or maximum solution efficiently using computing device? And how do we measure this efficiently? Like how efficient can we measure the algorithm? Anyone has, I'm sorry? Okay, you write a computer code, for instance, in C, in Fortran, in Java, in MATLAB, in whatever language you feel comfortable, and then run under different platform and see how fast, right? But that's not really something very intuitively appealing, right? Think about in some real industry problem that require you to solve a linear programming with 10,000 variables. How long does it take if you program?
A lot of iterations there.
Well, at least you need to find a way to quantify how the computational requirement scale as you increase the number of variables, right? In that case, there's a whole lot of theory behind it, which is called, for instance, some algorithm you can say scale as a polynomial function of what? Of the number of variables in the linear program, which is considered acceptable. On the other hand, you may have the algorithm that scale what? Like as an exponential function of what? Your decision variables, which usually is considered unacceptable, okay? And I think we do have some graduate students from computer science department, right? I think in that case, I think there's also like a formal definition of computational complexity in terms of what? Well, in big O notation, which means what? Something like, for instance, n is a number of variables in linear programming, and then big O means what? How your computational requirements scale with n, right? When n is large. And this big O notation is important. For instance, if it's a polynomial function of n, let's say maybe n q to the power of 3, then you'll say that's good algorithm. If it's something like a 2 to the power of n, you know it's computationally very expensive. That's exponential, right? And sometimes you may say of course, on the big O notation, you can say polynomial is better than exponential. And somewhere you can have super efficient. Maybe if you have an algorithm that scales log of n, then you can say that's much better than n to the power of 3. And of course, you can compare the order by just take the limit when n approaches to infinity to see which algorithm is better. That's like in theory, okay? And there's also another type of characterization on the algorithm that on the requirement of solving some problem, which is sometimes called you have a polynomial algorithm. Or sometimes you can say you don't have a polynomial algorithm, which is what? Well, it's not exactly, but can you elaborate a little bit on P and NP?
To be honest, I'm not that good in complexity myself, but P is considered a set of class that have their equivalent. You have an efficient algorithm for them. Whereas NP is considered a bit more difficult.
Okay.
Or you don't. I know you have NP complete, NP, but unfortunately I don't remember the slight entropy differences between NP and NP complete.
Okay. Okay, so yes, you want to add something to P and NP? Okay, so I think if you really want to get into the formal definition of P and NP, it's not really polynomial or non-polynomial. It's mainly about like ideal universal Turing machine, whether on that computer, what kind of requirement for algorithm to execute on a computer, you can make it, for instance, in terms of time and space usage of the complexity. It's mainly about, for instance, whether you expect the algorithm to run in polynomial time with the requirement of polynomial space as a function of decision variables, or you expect that to grow exponentially. For instance, for linear programming, it's considered a very important optimization problem that arises in many industry applications. So it has been studied extensively even during the World War II and then in the early 50s and 60s. And from computational complexity viewpoint, people want to say, is there any efficient algorithm to get to that? I think, how many of you heard about like a simplex method? Okay. Okay, so which is considered the most important technique to solve linear programming, which later we are going to talk a little bit about that. And that the complexity, in general, you can say in real world, it's quite efficient to solve large scale problems, but still the complexity can grow exponentially. On the other hand, you may say I can invent some polynomial complexity algorithm, but when you implement it, it's very slow on computer, so it just doesn't really add up. Until maybe late 70s and early 80s, there's an applied mathematician who invented interior point method, which is considered the efficient algorithm which guarantees to work in polynomial complexity and solve linear programming. And later we're going to talk about this original Kamak's idea of interior point method and also some modification to that, because the underlying mathematical idea is very inspiring for us to really understand what's going on, how we try to analyze the efficiency of a particular algorithm. But we probably cannot go very deep since most of you don't have good background in terms of theory of computation. But intuitively, you can say, I want to find an efficient algorithm that as the number of decision variable grows, my algorithm should have the required computational time should scale as a polynomial function instead of an exponential function of your problem, size of your problem. Any questions? Okay, so that's about linear programming. And if it's not a linear programming, you can say, well, then it's considered all kinds of other problems. You can say it's non-linear programming. So, but of course, in that case, we still need to classify optimization problems into different categories. For instance, you can characterize the decision variable as takes continuous value or only discrete value. Also, you can look at the constraint to say whether the feasible set is a convex set or not. If the objective function is convex and the feasible set is also convex, we can say we have a convex program. And later, we're going to talk about different characterization of the nonlinear models for optimization. Okay, so due to the fact that you can say linear programming problems are efficiently solvable, it is usually preferable if you have a real-world problem, you try to formulate it as a linear programming, if it is at all possible. And here you may not understand this point very well because you may say, well, I have a problem which doesn't look like linear programming at all. How it is possible that I can say I try to formulate the problem as a linear program? Well, sometimes there's no clear cut because this can be achieved at the expense of introducing, let's say, mode decision variables. I will have some example to highlight what it means. Even in these cases, the advantages of the linear programming model usually outweigh the increase of the size of the model. Meaning that, for instance, I have 2-variable nonlinear programming problem. I make it a 10 decision variable, but it becomes linear programming. Sometimes it is preferable to handle linear programming than nonlinear programming. And also nowadays, you have a lot of either commercial or off-the-shelf or educational optimization software toolbox. And sometimes you don't want to dig into the details because you're an engineer, you just want to have the quick and dirty solution, try to pick the right tool. But to understand some subtle point, to understand the engineering problem better, you may need to know a little bit about what certain optimization toolboxes can offer you on some concrete applications. So we are going to talk a little bit about that. However, in many cases, it is impossible to represent the decision problem, like optimize some cost with respect to certain decision variables that using only linear functions. And in that case, what we need to do, of course, is to have some creativity so that we can basically find some efficient way to handle the problem. I think the most important thing is you first need to really understand the field problem better and then try to find the right mathematical tool to write the optimization problem before even looking into what are the existing optimization tools that can solve the problem. Okay, so we are going to get into some examples to give you some idea how optimization problems can be formulated mathematically. Okay, so first example is about transport some hazardous waste. You can say a company is responsible for transporting some waste produced by 5 production plants to 3 waste processing plants. Okay, and then you may say, well, I have 5 plants at different locations. I have 3 waste processing plants that has to handle those waste produced by those 5 production plants. And the cost per unit transported from production plant I to processing plant J is denoted by Cij. Is that clear? That's something maybe you get from the field study. And then you say, well, the number of loads of waste produced by production plant is denoted by Li. Okay, so remember, before we get to the next slide, we have Cij. That means what? Cij is cost per unit transported from the production plant to processing plant. And Li is what? Like the number of load produced by the production plant. Okay, and then let's see. Suppose that we are interested in finding the solution that minimizes the total cost for all 5 plants. Okay, so what should we do? Well, we need to minimize the total cost, which is what? Well, just take the sum of all this Cij, right? But still, depending on what kind of decision variable, how you assign the production plant to what? The processing plant, right? And then you have the associated cost. And this Xij is something like the number of loads transported from production plant I to processing plant J. And then you have the unit cost, right? And then here's like how you make assignment on this. Okay, and this is something that happens all the way to many engineering applications. Like you have different, maybe if you say I have 3 people need to do all kinds of jobs, how much work I want to assign to each person, right? So that they can altogether then complete specific tasks with some constraints. And also you have, oops. I think you have this, and then what you need to do is to what? Write down the objective function, and then what? Write down the constraints. And the constraints include that you want to ensure all production plants transport all the waste, right? For each production plant, you don't want to leave any waste unprocessed. And non-negativity means what? You cannot assign something negative to from a production plant to the load has to be non-negative. Okay? And this part, is it clear? Objective, total cost, because this is like the unit cost assigning from plant I to processing plant J, right? And that's how much you want to assign, right? How many units you assign, and how to write down the constraints. Okay, because for each for each processing plant, for each production plant, because that's how much they produce, right? And then you assign this, the total load being assigned has to be equal to the waste that the plant produced, right? Okay, and this assignment has to be what? Non-negative. Okay, so is this a linear function of your decision variable? Is this a linear constraint of your decision variable? Yes, okay. In general, later we are going to say, in fact, this could also be written in a compact form that has matrix notation. Meaning that if you think about, I can basically, let me see if I can turn the light on this. Well, basically, I'm trying to say that you can minimize, you can say some C vector and then X, okay, and this X is a vector of all your decision variable because it's a linear function if you want to make it. And then the constraint, you can also say it's some matrix A multiply X, for instance, equals to some vector B. If you want to. Or maybe I should also have something like less than or equal to B. Okay, so in general, you can say a linear programming problem, you have linear objective function, you have like a linear constraint. And later we are going to say, well, this is actually a special case of so-called convex programming. Because a convex, you can say linear function, you can call that a convex function or a concave function. Either way, but it has some very nice property that the solution will be good enough to really be pursued by some efficient algorithm, meaning that in general, those constraints make the feasible set of the solution look like what? Look like partitioned by some lines, like some kind of, or you can say cut by some so-called polyhedral. And those terms may not be very familiar to you, but bear in mind you have to visualize by some geometry. And then because the optimal solution can only be on certain vertices, some extreme points. So the solution by so-called simplex method just try to what? Find a particularly good vertex as the feasible solution and then try to improve from there. Just jump around to find, eventually end up with the best vertex that gave you the optimal solution. And if you jump around in an efficient way so that you can end up not searching all the vertices in this polyhedral, you can find it very efficiently. And interior point method is actually take the opposite direction, which intuitively you can say, because it's called interior point, you never really get to those extreme solutions. You go from inside and try to directly get to the optimal solution, which is also a very smart idea if you can appreciate it mathematically. Okay, so let's try to look at the problem again. This is just a formal write-up on the optimization problem. We want to minimize the total cost for this weight processing and then subject to some constraints on assigning how much load each production plant needs to assign to the processing plant on the waste produced by this. And this 3 and 5, these are arbitrary. Basically, you can have maybe 10 processing plants, and then maybe you can have 15 production plants, and then the problem will have the very similar structure. Okay, any questions? All right, so that's the problem. It's actually easy to solve by inspection due to the absence of capacity constraints at the processing plants. How? Yes?
Each plant just sends to the lowest processing plant cost.
Okay.
And that should be it, because if there's no capacity, if it turns out that all 5 production plants end up sending to a single processing plant, they'll be okay because there's no capacity constraint.
Very good. Okay. So yeah, I think that's a good idea, because a lot of times you can say, well, optimization is based on some intuition and then try to make it formally. And this idea has something to do with what we call greedy type of algorithm. Why it's greedy is because just I try to do the best from my perspective. Like each plant, I just want to minimize my cost so that I don't care about other people's. Then if you don't consider any constraint, then that's some type of algorithm you can easily produce, which is usually efficient. On the other hand, later we have to come back, revisit whether greedy algorithm can produce good solution. If not, how to modify you not to be too greedy in order to get to the optimal solution. So now let's assume that in addition, at most, you can say U loads may be transported along some route from I to J. And then the absolute difference between the number of loads to be processed by any pair of processing plant may not be larger than some value delta. What does that mean? Well, that's something you try to figure out, like the marginal cost if you compare. For instance, should I work with Mr. Liu or should I work with Mr. Wu? And then I try to see if, like, I'm producing some waste, and then I try to see the marginal cost, the difference, and then try to basically make some compromise if there's a constraint, right? And then this is a different angle to look at this. And you can say, if I want to put some additional constraints on this, I want to ensure that no more than U loads are transported from I to J. Or maybe I want to ensure that the difference in the number of loads to process between plant J and some plant J prime is no more than some value delta. Okay, and these are maybe some real field requirement. If you think that, for instance, maybe your immediate supervisor wants to put some hard limit on what cannot be done in terms of the transporting the waste. And how can we write down this constraint? Well, the first one looks like this. And is this a linear constraint? Okay. And what about this? This is about the difference if I transport all these to some plant. This is about the total the total waste transported to this plant J, and this is about the total waste transported to this J prime. This difference should not exceed some value delta. Is this linear constraint? Why? Well, difference, you can say it's mainly about you take the absolute value, which means this is within minus delta and plus delta, and then what? Just change that to two different inequality constraints, and still each of them still is a linear inequality constraint, right? But of course, this one constraint, because you want to make it a linear constraint, what? Virtually you introduce more constraints, right? Because this is not really a linear constraint. Do you agree? But it can be converted to linear constraints. Okay? So we get into some point to make some constraints can be converted to linear constraints. And later we're going to say, well, in some cases you cannot. And we have to talk about that in some specific treatment. And of course, this is not a linear constraint. we have to appreciate that and then try to say it can be converted into linear constraints, because you realize that's the meaning of absolute value. And then you have the first part of the constraint and then the second part of the constraint, and then you can change the sign to make all these like less than or equal to inequality constraints. Okay? So you have this. And why I just ignored this?
Negative flows don't make sense?
Well, I would say it's because of this, the choice of J and J prime. Because I run those indices to compare everyone, okay? So it doesn't really matter if I put one side of the constraint. If you have the other side of the constraint and then I just switch this index J and J prime, it should satisfy. You get it? Okay, so in that case, in fact, it is linear constraint. And now you can say if I want to solve the minimized cost subject to the initial constraint that all these weights have to be transported, have to be processed by these three plants. And also each one has some capacity you cannot really exceed this U. And also you want to make sure that this assignment, all the weights transported to maybe a processing plant J, and the difference between J and processing plant J prime should not exceed some value delta. And also all these assigned loads will be non-negative. Okay? So still, by looking into the constraints and write it mathematically, we realize this is also a linear program. Any questions? Okay, so that's good. And now let's also assume that each of these 5 production plants is responsible for the transportation cost of their own waste. What does that mean?
Took it out from?
Okay, so that's a different consideration we have to think about. Try to, for instance, maybe we need to change the optimization problem completely, or maybe we need to study some other aspects, like changing the objective function or changing the constraints. So let's move on. However, the optimal solution to the model developed in the previous slide may give us different costs per unit of the waste transported for different plants. Okay, so in that case, we need to think carefully what do we want to do. This means some plants will not be happy with the overall minimum cost solution. Okay, so because of that, usually what will happen? They will talk, they will negotiate and try to find some compromise. You may say, well, I don't like the global optimal solution. I want my cost to be minimized. Okay. And in real life, you can have some kind of so-called multi-objective function, right? You may say, I want to maximize my salary. I want to minimize my commitment to, in terms of time and effort, to the actual workload. And these are conflicting to each other, usually, people say. Well, how to find the optimal solution that you feel happy about your salary and your workload? It's considered a very difficult problem. And if you can find an optimal solution to that one, please let me know. Okay, so in general, we have to study the problem thoroughly and try to find some engineering solution to all kinds of challenging problems. As some possible mechanism, you want to find a solution that makes the cost per unit waste similar between different plants. Okay? And that's not really doable in practice, but we have to make some mathematical abstraction, try to see how far we can go toward what we really want to do. So let's say we want to minimize the maximum cost per unit, the maximum cost per unit waste paid by the plant. That's something I would say, well, if a single plant can reduce the cost, the other one cannot. That, we know that's not a good solution. So we say the maximum cost for all the plants should be minimized. Make sense? But how can we model this? Well, here just try to think about what are the decision variables we have to introduce, or maybe constraints we have to introduce, or objective function we want to modify. Any idea?
Obviously, you don't consider transportation costs. You have to do that.
Okay.
That's a decision variable, of course.
Okay, so for instance, you may say, because previously we know like the unit cost of, and then we just try to calculate the assignment, right? And now we need something more in order to optimize whatever we want. Of course, you can say, well, I introduce whatever decision variable immediately related to what I want to optimize. If that's the case, then I can just say cost per waste transported by a particular plant I, and then I have this Ki about the cost. And additional constraint I want to say is about this. This is like, think about for each plant I, you have all these costs associated with the load you assign to that, and then here's the load, the total load, and then you have the unit, you have the unit cost per waste transported by this plant. Okay, so now this is the maximum value we want to minimize. Okay, and of course we have some previous constraints. You can easily put it down. Okay, those constraints we just mentioned, they are actually linear constraints. Now the question is this linear program? Is this like a linear program? Is this a linear program optimization problem? No, why not? Because we want to maximize within these 5 values, K1 through K5, want to pick the maximum, and that's finding maximum or minimum within discrete set is not a linear operation for sure. And in general, if this set has many different values, theoretically speaking, you have to basically check each value, right? And that's not really an easy task, especially when you have to face, for instance, different combinations to do the job. For instance, let's say we have 12 students here in this classroom, okay? And then, and 13, including a student remotely connected to our classroom. And then let's say maybe at most 3 students can work together on a particular assigned project. And I want to know which individual or the team can do the best job for that project. Okay? And then how many possible solutions I'm looking at? Not exactly. I would say more than that. Because I can assign a single student to work on that. I can do what? I can ask them to work together as a pair, or maybe as a team of 3. So essentially, it's what? 12 plus 12 choose 1. Okay, very good. So that will be some large number, even though we are talking about only 13 students, 12 or 13 students, right? So that's some problem. Later we are going to say it's considered so-called combinatorial problem, meaning that we have to consider all these combinations. And in fact, there's no point that you let the computer to run all the possible combinations. I try to find the best one. If the problem has this kind of structure, you cannot find efficient algorithm, then you have to look into not the optimal solution, but close to optimal solution, but within your computational load, computational resource, you can find it efficiently. Okay, so now let's go back to this problem. This is not a linear program, but can we make it a linear program? Well, I see some of you shake your head saying, wow, that's hard. Okay, so in general, there's no way we can just examine the problem and determine yes or no, or even write a computer program to do that. It's very challenging. However, if you have some experience in terms of the mathematical property of certain problem structure, then you can answer this question. So this problem is nonlinear. You all know why. Is it continuous? It is not continuous, right? Meaning that, for instance, if I try to assign 2 students work together, I cannot assign 1.5 student. And also, there's no value associated with that, with certain continuum, meaning that this can only take some. But the maximum function in itself, you may say, well, that's something like a nonlinear operation. Is it differentiable? Why not? Okay, if you know it's not continuous, you cannot differentiate. Okay, so here's the full nonlinear programming problem. We can write it down. We say, for instance, minimize the maximum unit cost among these 5 plants. And where this K is defined this way, that's the unit cost for each plant. And then subject to whatever the constraints we introduced before about like the total load constraints, the individual assignment constraint, and then the load difference constraints, and the non-negativity constraints. These are things we have to take care of. Okay, but then how can we solve this problem intuitively?
This isn't a particular large one, so you can just brute force it.
How? Can you
Go over all the possible combinations.
go over all the possible combinations? In what sense? You mean? Because it's not just assign a particular production plant to a particular processing plant. You need to specify how much load, right? And somehow it's not just like a discrete combinatorial problem. It has to do with these constraints and the objective function. So of course, intuitively you can say, well, these things are linear constraints. We know that only change the feasible set into some specific convex set, some structure, which we know how to take care of later. The difficult part is this: minimize the maximum value of this Ki. So we have to think about, can we make it a linear one? Okay, and you can say, wow, it's difficult, but there's a trick that you can say, I define a new decision variable, which is called just the maximum cost paid by any of these 5 plots. Okay, but still the same problem. And then still we don't see how to proceed, right? But we just say, well, this variable we can minimize, that's linear. Then what will happen if we do it this way? Well, the objective function is linear function now, but what happens to the constraint?
Probably broke a few of them.
I'm sorry?
You broke a few of them.
Okay. Well, straightforward, if you look into this straightforwardly, then your constraint will become nonlinear. Do you agree? On the other hand, yeah, we have to ask a question like this. Did we really gain anything by doing this? Yes? No?
Does it depend on your constraints?
Yeah, of course. On the surface, we need to introduce constraints to link this K to individual, right? Individual, we know how to define that. But this K, how do we link that? We need this constraint. Okay, so original objective function now becomes constraint. That's like take the maximum value of this. Okay, is this a linear constraint? No. So basically, what I mean is that when you formulate the problem, of course you can say the objective function is now a linear function. On the other hand, the constraints become nonlinear. Doesn't really make much sense to say the problem becomes easier. Okay? And now what? Now we have to say, well, in general, if you have a nonlinear problem, by just manipulating this, changing the objective function from nonlinear to linear, in fact, you may change the linear constraints to nonlinear constraints. That wouldn't really buy you anything if you just do this. And suppose that we allow choosing K larger than necessary. Okay, so we could say, well, I can choose K even greater than the maximum value of that. What will happen? And if you think about, this does not appear in any other constraint, and it is the only term in the objective, then this constraint will be binding in the optimal solution. What does that mean? Well, like what Sarah just suggested, if you just do something like a brute force, you can basically solve the problem and then try to see what, if it satisfies this or not, if that's really the maximum or not. If you check, well, I cannot do better than this, then we stop. And you know that's basically how you get this constraint crossed. Okay? But remember, this additional trick has nothing to do with some systematic way of converting a nonlinear program to a linear program. It's just the problem in itself possesses some additional property for you to treat like this. So finally, you have a single constraint like K is greater than the maximum of this, which is equivalent of what? 5 constraints, right? And these 5 constraints are linear. Okay, so what? So I managed to change the problem into a linear program by introducing additional decision variable and add 5 more constraints. Okay, so now can you see the difference? like in real world problem, of course, sometimes the problem, when you formulate in its original form, it may not be a linear program at all. But some problems do possess certain property you can convert into a linear program at the price of what? Either introducing more decision variables or adding more constraints, even though those constraints are linear, but you actually increase the size of your optimization problem. Any questions?
So the optimal solution of this problem is different from the previous one.
Why?
Because you change the constraint.
Well, but now we can actually get rid of each ki, right? We just say, well, we want to find the k that's greater than each individual. Greater than or equal to. And if I can satisfy that, then the solution to this should be the maximum, right? The solution to this k, capital K, should be really the maximum. And you cannot be better than this, satisfying all the rest part of the constraints.
But I think the original constraint, the k is not possible larger than the maximum one.
Well, larger than or equal to, like no smaller than, to make it more accurate.
I mean, in this one, the optimal solution k probably can be larger than any of ki. Yeah.
Well, but would that be possible? If that's the case,
well, I don't see why it cannot be possible. Why?
Well, later we will see that for linear objective function and linear constraints, usually we say those inequality, when the equality constraint is in effect, we call that active constraints. And later we are going to see that in general, this cannot be all inactive in the optimal solution. So that's some property very interesting to linear programming. Like the solution, optimal solution has to lie on certain vertex, which is
one of this constraint must be
active, yes.
Okay.
And that's basically what I meant. And intuitively, that makes some sense because if you can do better than without using any of these constraints, then this constraint you don't need to put there, right? Meaning that, for instance, if I say, don't come later than 8 o'clock, because the class starts at 6, you should come at 6, then, for instance, that constraint will not be in effect, so you can safely remove that. Make sense? I hope so. Okay, so now, remember this k should be greater than this, and we have one new variable for the objective function. We have more constraints associated with that, and then we have 5 new constraints and the old one, and that's a full linear program. That's equivalent to what we want to maximize for the maximum of the unit cost for all 5 plants. Okay, so any questions? Okay, so let's take 5 minutes break, and then I hope we can wrap it up and then try to also summarize what are the important aspects for modeling the optimization problem from maybe a few more examples.
Go back to the last slide.
So the previous slide, sure.
First of 5 constraints. That means that if we try to find the optimal solution, then probably at least one of the constraints must be active. active.
Yeah.
But because we add some more, the following more constraints.
Oh, you mean here?
Yeah, that you know.
Well, without this, these 5 constraints, one of these should be active.
Yes. But
With this, I would say, well, you can make the problem infeasible, meaning that sometimes you don't have any feasible solution. If you still have a feasible solution, then then this will not be, then the active constraint cannot become inactive. You see my argument?
the active. So you mean with the following, the last 4 constraints,
Yeah.
the last magic constraint?
Yeah.
Probably. So I mean, with those constraints, the optimal solution of this problem is different with the original.
Yeah, it can be different, yes.
So that's my point. So
Yeah.
how do you convert it to this?
But of course, the active constraints, the active constraint on this may change. I agree, but you can say, well, but you cannot say, well, all these 5, none of these will be active. That usually will not be the case. But even if that's the case, still we need to look back to the original problem itself to see if, in that case, whether this case is feasible or not. Meaning that, for instance, these are values you can compute, right? And then you can have a real value greater than that, right? And then that satisfies all this, okay? And that means what?
That means this case rather than all the possible.
Yeah, that means the original problem is not feasible, right? And that's basically my answer. Then you don't have any solution. Like you want to find the maximum for this, to minimize the maximum cost for these 5 plants. Then there's no such feasible solution. Then no such feasible solution exists if these constraints, all these constraints are inactive. Basically, that's my explanation. I hope you get that point.
Each one details a certain cost function. Okay. And this is the load I want to deliver to. I'm going to have a transmission bar, but this one might actually be, more efficient, or let's say less efficient. Okay, but this one is less efficient, but it's closer to the load. This one might be the most efficient, but I don't want to connect to that point right here. But what I'm trying to reinterpret your problem.
Yeah, I think it's better this way. Then you find your own problem, yeah, and then try to.
What I was trying to turn around and say, imagine this, like I got right here.
Okay, good.
And I did like a triangle. I have 3 tie points.
Yeah.
They're load points. So I'm not going to say
Okay.
individual customers.
Yeah.
Major exchange points of load.
Yeah, I think later, I hope every student will have the opportunity to find a problem I explain to the class about it. Yeah.
This plan here,
Yeah.
and the cost of transportation to us would be the transmission losses.
Okay.
Right, in the grid.
Yeah.
Right? So you have to balance the grid cost to transport the power versus the heat rate of the plant or the
Okay.
efficiency of the plant.
Okay.
Right? And that's what I was kind of just talking about.
Okay.
That's similar to your problem, but I'm a long way from formulating it.
Well, sometimes you have to simplify a little bit so that it can be mathematically
Well,
tractable.
they've already done it
Yeah.
a gazillion times.
Okay.
They got what's called B matrix. They call
Okay.
which model of transmission.
Okay.
And then they got what's called incremental heat rates on each unit.
Yeah.
They optimize it every day. They're constantly shifting a
Yeah.
generation based on
Okay.
these programs.
Yeah, of course, later I hope you identify a problem and maybe put that into the cost term product and like. Okay, so like what I mentioned in the beginning of this course, when you read the syllabus, you will see that this course actually is different from other type of courses where we don't have midterm exam. We do have final exam, but I think we emphasize a lot on homework assignment and computer assignment, where you do need to use computer to solve some optimization problem. And also we do emphasize on course project, where you want to identify some interesting problem from your field experience, from your research problem, from whatever things that you feel you can apply optimization skill to solve, and then try to contribute to some degree about solving real engineering problem by applying optimization algorithms, methods and algorithms. And hopefully some of you may invent more efficient algorithm or solving some outstanding optimization problem and even write research paper using some techniques that you learned from this course. And usually I would encourage you to make your own proposal on what topic you want to do. Otherwise, I may assign some topic that you don't like, which I think according to the schedule, usually we assign term project by the end of February. And then so that when you have a little bit knowledge about what optimization is about, you have some knowledge about how the existing techniques can be applied to some engineering optimization problem, then you can start working on that. Okay, so that's pretty much about linear programming. And here, let me just briefly recap what do we mean by linear programming. Of course, the objective function has to be linear, and the constraints have to be linear. And in this case, you can say this can be right in terms of vector c multiply vector x, like an inner product. So that's the function f, which is a linear function. And if you have a function with more than one linear part, which is really not a linear function. Okay, so let's look at some other example where you can see sometimes it's really difficult to make the problem like a linear programming. Okay, so let's consider some warehouse or facility location problem. And in this case, we want to choose a set of locations from a large set of candidate locations. For instance, you may say, we want to build airports. How should we decide the locations? Okay, and here is about the warehouse. And there are many constraints and considerations. For instance, you may need to know the requirement and try to distribute them more or less evenly somehow. And in this case, because you have a large set of candidates, you can only choose a subset of this candidate. So it's highly related to in machine learning called feature selection problem. You have a bunch of features, you only want to select a subset of important features to do pattern recognition, to do clustering, so on and so forth. And what you need to do, of course, is to solve the problem in some optimal manner. And in fact, this is actually so-called mixed integer linear programming, meaning that the decision variables include like some linear objective function, but some set of the feasible solution may only take integer values, like 0 and 1. So that's the structure of the problem. And if we talk about the candidate locations, they are often found by solving some location problem in a two-dimensional plane. And in this case, location problems, we may basically try to say I can arbitrarily put within some region. I don't consider some physical constraint, like I can only choose 6 possible locations and put 2 airports on those things. I say I can choose any location I want from the state of Louisiana. For instance, that may make life easier sometimes. But still, it's not really something we can make it really manageable. Here's one particular warehouse example. We want to locate a new warehouse from which it will ship the product to 4 different customers. And the location of these 4 different customers are in like the XY coordinates like this, 5, 10, 10, 2, 0, 12, 1, 1. And also they have different number of shipments per year given by this, like for instance, customer 1 needs 200 shipments, customer 2 needs 150, customer 3 needs 300, 200, and customer 4 needs 400. And these are just some numbers for convenience for you to think about. What do we need to optimize? We need to put a location labeled like this, okay? And then this is the location of the customer, and then that's the shipment, right? And we want to put a warehouse so that what?
We would like to have the warehouse in a
Close to all customers somehow.
it's got to be.
Yeah,
you can put it in the middle.
yeah, it would be nice to put it in the middle so that the overall distance to travel in order to ship those things will be minimized somehow, right? Okay, so we have to first think about what objective you want to achieve and then think about how to really optimize that. Suppose that the shipping cost per shipment are proportional to the distance traveled. Of course, that's a mathematical simplification, but sometimes you can say it's realistic enough to begin with. And then the company wants to find the warehouse location that minimizes the total shipment costs from the warehouse to these 4 customers. Okay? So what are we going to do?
Would you want to do some type of weighted, use the number of shipments to multiply against the distance from the warehouse to each one of the customers?
Okay, yes, that's a very good suggestion. So we need to formulate this problem as an optimization problem where, for instance, depending on how we measure the distance between the warehouse location to each customer's location, right? And a natural way to interpret distance, of course, all of you know Euclidean distance, which is what? Which is like what's the physical meaning of Euclidean distance? It's just from point A to point B, you measure that, right? And sometimes you may not be familiar, but these are also possible distance metric we can talk about. For instance, this Manhattan distance metric, it means what? Very good. It's like you can only go along XY direction, so you measure basically the difference in X and Y locations and take the sum, right?
And you can't cut through somebody's property.
Okay, very good.
Take the streets.
Okay, and decision variables, of course, in this case, we can put warehouse on any any location in XY coordinates, then it's this XY, and distance between warehouse and customer 1 located at 510, you can say this is Manhattan distance, and that's Euclidean distance. Okay, so depending on how we use different distance metric, objective function can be very different. Okay, so now let's look at the optimization problem. We want to minimize this total distance, for instance. Let's assume that's what we want, subject to what kind of constraint? In this case, we don't have clear constraint. We just say we can put whatever location we want for the warehouse, okay? But what if you look at this objective function, what's this? Is this a linear function? Yes? No? Not sure. Okay, that's a good point. It is, of course, it is not. And Mr. Liu just said it might be, we may want to convert that to a linear function by introducing what? Some constraint, or maybe introduce a new variable. Okay, good. And what about the second one, Euclidean distance? That's clearly nonlinear. And I think Mr. Liu probably is not sure how to really convert that one. Okay, so this is some problem we see that we cannot say by just introducing additional decision variable, adding new constraints, we can always handle the optimization problem by linear programming, even though preferably if we can make it a linear program, usually we know it's easier to solve using computer. Okay, another example. Let's say some Monroe County is trying to determine where to place its fire station. The central locations of these counties, major towns are these locations. Well, the county wants to build the fire station in a location that would allow the fire engine to respond to a fire in any of these 5 towns as quickly as possible. So what's the difference between this problem and the previous one?
Well, if you're taking whole towns,
okay,
you might be able to use that straight line approach with this.
Yeah.
First not only more about minimizing the cost.
Okay. For all these customers, you have to satisfy. And here, what's the difference? Well,
But he makes a good point,
yeah.
the far away guy, because obviously you might want to weight that.
Okay, yeah, I guess in the previous problem, we take the sum of the distance. Basically, we take the sum of the distance to measure like how much total cost do I need to commit for putting a warehouse at a location, right? And in this case, it's not really total distance. It's about what? Yes.
Minimize each path.
Okay, I want to minimize the distance to I want to find the minimum distance.
To get to the fire quicker.
Okay, to get to all these towns quick. Okay. So if we want to formulate this as an optimization problem, then the objective is not really defined precisely. Like I think all of you have your own opinion on what you want to do. Like how should we choose the objective function in this case? In many cases, I would say you, as an engineer, you always face the problem like, do we have sufficient data to formulate the optimization problem? Right? And sometimes you have to compare this situation to, for instance, like your own problem to this warehouse problem or waste transportation problem. What's the difference? Usually for waste transportation problem, you know the cost is proportional to like the unit production, and then you have some way to build up your objective function. And in this case, for instance, you want to say I respond to the fire alarm to each place as quickly as possible. That's really something we cannot formalize. But of course, like some of you suggested, one way of doing that would be just to minimize the distance among the location of the fire station to all the possible county, all the possible towns in that county, right? That's something maybe I think most of you agree as a legitimate objective function we try to minimize, even though it's non-linear and also it's not so easy to optimize. And later we're going to try to introduce a bunch of algorithms or computing methods to address this kind of problem. Okay, and let's say there's a company just running advertisement on soap operas or football games. Let's say each soap opera may cost about $50,000, and each football game and these are all the comparison of the cost of advertisement. And for the football game, maybe 100,000. Okay, so and anybody will watch Suns game this weekend?
Oh yeah.
Raise your hand.
Oh yeah.
Wow, quite a few Suns lovers. Okay, so I guess this is not a really good figure to compare if I think some students don't watch soap opera at all and don't watch football. But let's say we want to study at least 50 million men and 60 million women to see, they want this many people to see the advertisement. And how many ads should they purchase in each category in order to achieve some kind of. And of course, you want to say how to really save the cost in such a problem. And sometimes you may say, well, is this really an optimization problem? How do I really make it a mathematical, formally write it in a mathematical way? Okay, so whenever you have some real problem, you always have to think about what are the decision variables, right? And what's your objective function? How do you link your objective function to the decision variables? What are the constraints? How to write it formally so that we can solve that. Let's say decision variables are number of advertisements in soap opera and number of advertisements made for football game, okay? And let's say if as soap opera as are bought, they will be seen by this many men and this many women. Well, you may ask me, how do I come up with this number? I don't. Well, this is actually adapted from some textbook in operation research, where they just did some calculation based on small-scale survey and try to cook up with some interpolation where they believe that women tend to pay more attention to soap opera than men, which I don't know if that's the case. But I think, for instance, in this classroom, we have disproportionality about women in engineering field, which unfortunately is the trend in the US industry, engineering industry. Well, the problem is that sometimes we have to model that if I have, of course, football game as brought, they may be seen by this many men and this many women, and look at the difference. The leading factor is about, they say that this is square proportional to like how many ads you bought. And then that's like some leading factor, and in this case, like men tend to pay more attention to football game than women, which is true only to some degree to, I would say, to some people who are in this business. Let's assume that's the case. And if you think about, in this model, what is lacking is about what? The number of men and women seeing this looks like what? A linear in the number of ads. Oh, if you think about the square, and if you have another assumption which says just the number of men increase linearly in terms of the number of ads you bought, which one is more realistic, square root or linear? Square root, why?
Because a lot of the people watching football will be watching anyway, so
okay.
It's not like every ad gets that many new reviewers.
Okay, so you want to model some kind of saturation effect, okay? And anything else? Yeah.
Constraints on it, I think it's not impossible to kind of linearize this.
Okay, I think that's another aspect, I guess, because yeah, there might be some other constraints, but here it's just about if you want to buy more ads, if you want to buy more ads, whether you believe people watch that will be linearly increasing in terms of the number of ads you buy. And I would say probably I'm more or less pessimistic, like what Rustin suggested. I would say, yeah, a non-linear model could be more appropriate. And look at this. that's one possible formulation on this advertising campaign, something like how do I determine the cost of buying number of advertisement in soap opera and football game. And then these are constraints like this S and F cannot be negative, and then we want this to reach at least like 40 million men and 60 million women to be targeted based on this number of men and women, and then we want to minimize the cost. Okay, so is this a linear program? No. And do you believe there's an optimal solution to this problem?
Yes.
Why?
Well, if those constraints are really true.
Well, intuitively, what you can do is to say, well, I have these feasible sets, right? And then just put that as a function of S and F and draw the level set of this objective function, okay? And then I have these constraints, right? And then, of course, I can basically put equality there, say, assuming that's the active part. And then basically, I can highlight what are the feasible sets. And graphically, I can basically try to see within the feasible sets how this objective function change based on the level set. You can do a contour plot. If it's two variable, you can do a contour plot. And then you can see how the level set change, right? And then somehow, maybe at the boundary or maybe inside the boundary, you can have maybe the optimal solution, hopefully. And intuitively, we all believe we should find optimal solution by doing that. Okay, so I do have a computer assignment for you to just get your hands dirty in terms of doing this kind of exercise to visualize constraints. And basically, we try to say, well, if you can satisfy all these constraints, then it's a feasible solution. Okay, and then, of course, the optimal solution has to be feasible. And in order to visualize, you can say, well, I change the value of S and F and to make it equal to 1, 2, 3, so that I have different level set, okay? And then by changing the level set, it will intersect with this feasible region. And then somehow I want to see to some extreme, where should I go? Okay, so now let's do some modification here. Suppose now that the number of women, of course in the unit of millions, reached by F football as and S soap opera as will be modeled by this. This is 7 square root of F and 20 square root of S minus 0.2 square root of Fs. But why we want to subtract out this 0.2 million? Targeted by both football and, I'm sorry? Okay. Okay, so what's the underlying reasoning behind this? Okay, so basically an individual could be targeted twice, right? You don't want to double count that, right? Is that realistic? I would say so, because usually there are some correlations. And some people may like football and soap opera, and some may be resistant to any kind of targeted advertisement. Okay, so now, of course, let's get into some formal description of optimization problem. Okay, I think this is the most important ingredient that I want everyone to pay attention. In general, when we say mathematical optimization problem in terms of nonlinear programming, in general it means what? We want to maximize or minimize some objective function f involving not just one variable. In general, n variables which is actually a nonlinear function, but for any input vector x, you will get a real value that you want to maximize or minimize, subject to many different constraints. And these constraints can be equality or inequality. Okay, so either the objective function is nonlinear or the constraints are nonlinear. We call that nonlinear programming. Okay, and sometimes you may say, I don't have some constraint like this. I just say, I just want these values to be any value, any real value. Then that means no constraint. Or maybe sometimes I just say I limit my discussion to all positive real number for x1 through xn. That's similar to no constraint, but the constraint is actually just non-negative. Okay? So we can have so-called unconstrained optimization and constrained optimization. And we can have linear programming and nonlinear programming. Which one is easy? Usually I would say linear programming is easy. But do we want to start from linear programming? Usually we don't. Why? We want to start with something intuitively simple. But in linear programming, it's not because of the bunch of constraints. So we want to start from what? Unconstrained optimization. We say, well, and also we want to start from something really simple, just one variable. Okay, and then what? Maybe in that case, if it's a linear function, can we optimize? No, why not? Because a linear function either is flat or monotonously increasing or decreasing, doesn't make too much sense. If you have a one variable you want to optimize, it got to be some nonlinear function. So first, maybe we want to talk about how to handle that. Unconstrained optimization for one variable, and then maybe for multiple variables, and then constrained optimization. And specifically, we may dedicate some effort to explain about some important property of linear programming because of the constraint. And also, we have to talk about how to convert the constraint into part of your objective function. And sometimes that's intuitively appealing because originally you have constraint, and then you put that into your objective function, it looks like you don't have any constraint. And sometimes you may say, I want to go the opposite way because I want to introduce more constraints so that nonlinear program become linear program. Okay? So in all cases, we need to basically consider about what we mean by optimal solution, right? The optimal solution. And later we are going to talk about local optimal and global optimal. I think some of you already know because during the introduction, some already mentioned certain mathematical terms that we are going to use to characterize the solution for some problem. And look at this. We have, in general, more than one constraints. So sometimes we use H for equality constraints and G for inequality constraints. And of course, these are just for notational convenience. And the set of points satisfy all constraints is called the feasible region. And sometimes we call feasible set. And then a point X that satisfy all constraints is called a feasible point. And sometimes we call that a feasible solution. And feasible solution just means something like you have a problem, I can give you a plan. Is it optimal? We don't know. Okay, but if you exhaustively enumerate all the plans, if the feasible solution is a discrete set, then you know it's optimal. On the other hand, if the feasible set is a continuous region, you got to justify by what? By mathematical property, by derivative, by differentiation, by knowing that in the neighborhood, no better solution can be better than this point in this neighborhood. And then I can expand that. If it's not good enough, if I am good in this neighborhood can grow arbitrarily large. That's because of what? Some property of the function, for instance, convex or concave. Okay, so now we are going to talk about some important property about like optimal solution. Of course, a feasible solution X star with the property that it is no worse than any other feasible point. This is called what? The optimal solution if I want to maximize f. If I want to minimize f, then of course the optimal solution should be no larger than any other value of x. And of course you may ask the question, is optimal solution unique? Not necessarily, right? For instance, I may say, well, if you can do as good as another student, they are equally good, but this is the optimal solution, but of course you can have many feasible points satisfy this property. Okay, so I guess these slides are available on Blackboard, and usually what I suggest you to do is to read the textbook first and then look at the lecture notes, try to fill in the gaps. And another practice that I find extremely useful is that usually I would suggest each student take recitation notes, try to fill in some gap, because sometimes I may provide lecture notes and sometimes I may not provide complete notes for the lecture material, so that I will at least try to see if there's a good way we can recap the material based on the communication on Blackboard. So I guess starting from next time, I will ask any student to volunteer taking recitation notes and send it back to me within 1 week so that I can post that on Blackboard. Usually I will make comments to the recitation notes. And then other students can also make comments, suggestions, and discussions on course Blackboard. And I feel usually that's a very good learning practice. Any questions up to this point?
You said we had a homework assignment or something?
Yes, it's on Blackboard. We do have first homework assignment, which will be due next class, and I also posted a computer assignment, which will be due 2 weeks from today.
Yeah, because I don't have my software yet. I ordered it and still haven't gotten it yet.
Okay, so let me know if I can be of help. For instance, maybe just tell you there's some. I think if you are a UNO student, you probably have remote access to MATLAB or some other facility based on. Maybe I don't know if for instance, the UCC help desk may provide you some information on that. And the engineering building has some computer with MATLAB installed. And if some of you may need occasionally on some part of the MATLAB optimization toolbox, I will try to figure out a way. If you only need some part of the file, I will try to give you that copy. But because of the copyright issue, I probably shouldn't distribute to all of you. Okay, so I guess that's pretty much for tonight. We only covered the basics of the mathematical optimization problem. I made some concrete definitions on, for instance, how to formulate the problem, how to write down the objective function, how to put the constraints into practice. I want you to read the mathematical review in part 1 of the textbook. I also work on the homework assignment, which will force you to understand about Taylor series expansion and vector type of gradient and Hessian and things, how to take derivative and how to write in mathematical language about the limit. Later, we are going to use that to characterize optimization problem. And also, I would like you to start looking at the computer assignment and try to use graphical visualization of the objective function in terms of level set and visualize the constraints. And basically, you can just follow the steps and write MATLAB program to plot the objective function and constraints and try to answer the computer assignment. Even though it's due 2 weeks from tonight, still you can start working on those things. And also, my office is at the engineering building at 819. And also, I would encourage you to talk with me if you have difficulty working on some course material assigned problem, and also take good utilization of the course Blackboard, especially spend some time reading the textbook and also try to also put your questions on course Blackboard and the discussion forum so that some students can, I think they can actually form some informal study group and discuss about this using all kinds of devices, interactive media devices that are available to us. Okay, so that's it for tonight. And if you do have some questions, I will be here for additional few minutes. Feel free to come by. Thank you. And any questions from the other end?
No, sir. One thing though about MATLAB, if somebody doesn't have MATLAB, I know there's Octave and also FreeMat, which are similar and open source.
Okay, yeah, thanks for the information. I think some of you used Octave before, like Rastin, right?
I've never used it.
Okay, so, but you know that, I think that's somehow more or less equivalent to a lot of functionality in MATLAB, and if you are familiar with MATLAB, you probably can easily get to that. But the difference is that some optimization routines have not been exhaustively tested in Octave. And also I may have some additional toolboxes which I exclusively use in MATLAB that I don't have time really to test under a third-party software. So we'll see. If you do have some difficulty accessing MATLAB or optimization toolbox, please let me know. I will try my best to find some accommodations for that. For instance, maybe let's say you can maybe use my license code for some period of time within limited computing device, and later you have to really purchase a student version or maybe try to find university facility to accommodate you computing requirement. But overall, I would say it is a very useful software that you may want to use in the future. Okay, so anything else?
No, sir.
Okay,
That's it.
okay, thank you, and have a good evening.
Dr. Chen,
Yeah.
not looking